students, internet world, cloud, whoever I may be talking to right now. It's MoNaCo.
And Milks.
We are in our 5th unit of study, moles and stoichiometry, which is just about counting and measuring in chemical reactions and equations.
Basically. We are going to be on page 5 and 6 in our packet today, and we are going to learn a little bit about mole theory.
My favorite is history.
You do it. So it's you know what, Mr. MoNaCo, why don't you run with it?
Yes. Amedeo Avogadro. He came up with a mole theory back in 1809 or something like that.
Or late 1700s.
He was born in 1776, died in 1856, but 1821, I believe, is when he published his paper on mole theory after somebody else published a paper on gas law theory. So another guy we'll see later on.
I forgot to tell you, Alex Trebek called. He wants you on Jeopardy.
I know, my wife tells me that all the time, but ain't nobody got time for that. So he figured out that equal volumes of gas at the same temperature have the same number of molecules. And so he ran with that, and he said this is a mole. It's a tool nowadays for counting chemical reactions and results, computing results. So we use the mole in our recipes for chemical reactions to get to grams so that we can measure things and weigh them out in the lab and predict an amount of substances needed or consumed in a chemical reaction. We use this mole exhaustively as a stepping stone to get what we want out of a chemical reaction in a lab or in an industrial process, et cetera, et cetera, et cetera.
And it proves to be very accurate. If you watched our intro video, we were on the money.
Yeah, as a matter of fact, we were right on the money.
Yeah.
Perfect. Yeah. We're so wavy.
Yeah, bad wavy, yo. So the mole, 1 mole of any gas at STP, standard temperature and pressure, will occupy specifically 22.4 liters.
And that's what Avogadro came up with in the first place. STP is 0 degrees Celsius and 1 atmosphere of pressure.
Right, so we have an even playing field.
Right, so all gases at the same temperature and pressure occupy the same amount of space, pretty much.
Right, so 1 mole of carbon dioxide at standard temperature and pressure is
22.4 liters.
And 1 mole of hydrogen gas at the same standard temperature and pressure would be
same volume, 22.4 liters.
There you go.
Any gas, and we're not talking about gasoline, we're talking about the gaseous phase of matter.
Right.
Anything that forms a gas will occupy this volume and be 1 mole at that temperature.
Right. Now this next piece, the mole and how it's related to mass, is where we get to where we need to get in all of this stuff. So specifically, 1 mole of any element equals the atomic mass of that element. Right. Find that on a reference table.
Periodic table.
Periodic table, upper left-hand corner.
Yeah. Right. Because you can't, not everything's a gas, so you can't measure a mole with volume with everything. You need a mass to do it because most things are solids or liquids.
Easily most things.
Most things.
Periodic
sure.
Table,
so they related the mole to the mass of atoms.
Right.
And that's all there was to it. So
nice.
a mole of carbon
is going to be 12.01 grams.
We always round this when we do computations in our class.
In class we're going to round it up, but that's the actual number that's on the reference or on the periodic table. So we wanted to put that in there.
And that's a mole of lithium would weigh whatever its atomic mass,
6.94 grams.
And a mole of nitrogen, 14 grams. And this is actually really useful for a chemist or anybody working in a chemistry lab for that matter, because you now have a way to weigh out 1 mole of atoms.
Right.
On a scale.
Right. Because I can't count them.
Absolutely.
They're absolutely way too little.
Way too small, and there's way too many of them in 1 mole.
Yeah, but think about that.
Never going to happen. But you can quickly and efficiently and accurately count them by weighing. Kind of
fabulous.
There's our particle relationship. It's a counting number. You need to remember that the symbol Na is for the number Avogadro. It's 6.02 times the 10 to the 23rd. Particles equals 22.4 liters of gas at STP equals 1 mole.
Right.
These are the constants. This is like what it's equal to, all the way steps along the way.
And we're not going to use this huge 6.02 times 10 to the 23rd number all too often. It's more of a theory thing, right? But I do remember from back in the day, if we had like that many basketballs, we lined them up, touching in a straight line.
We would go to like Alpha Centauri or something.
Or go around our planet like something like 4 times.
Right. If I had a mole of marshmallows, it would be enough marshmallows to cover the entire surface of the planet, including the oceans, 5 miles deep.
ridiculous.
That's how high planes fly. Seriously. Okay, so it's a gigantic number that is really hard to comprehend.
Right, and if you see on the left, it's a trillion.
At least, maybe more.
Right.
I don't even.
Right.
I'm not even going to bother.
Right.
So why is it useful? Who cares? What's the point?
Well, because now, like we said, we can figure out how many atoms are happening. We have in the lab by measuring them in grams.
Right. So it's a practical tool.
Right. And these things in these balanced chemical equations don't go gram for gram, but they do go mole for mole or atom for atom actually.
Ratios.
And that
Right.
number we need,
Right.
So if we have 2 moles and 3 moles, we can kind of cancel that moles
Right.
out 2 to 3.
So chemical reactions happen in simple whole number mole ratios, right? And these ratios are the number of moles of each product or reactant. So we use mole ratios to relate products and reactants. Now we can convert those mole ratios into masses to relate products and reactants. So I can actually do chemistry in an industrial setting or in a lab. There you go. That's it. So you got to know your mole theory. You know what it is, why we'll be using it so much. Anything else, Mr. Milks?
Oh, we're good. See you guys.
Thank you.